Continuity at a specific point is a fundamental concept in calculus, describing a function's behavior without interruption at that location. Intuitively, a function is continuous at a point if you can draw its graph at that point without lifting your pen. Formally, a function f of x is continuous at x equals c if and only if three conditions are satisfied simultaneously. First, f of c is defined. The function must have a value at x equals c. Second, the limit exists as x approaches c. The limit of f of x as x approaches c must exist. This requires the left-hand limit and the right-hand limit to both exist and be equal. Third, the limit equals the function value. The limit of f of x as x approaches c equals f of c. Breaking down the conditions, condition 1 fails if f of c is undefined, for example, if there is a hole where the function isn't defined, or a vertical asymptote. Then continuity fails immediately. Condition 2 fails if the left-hand and right-hand limits differ, which is a jump discontinuity, or if one or both are infinite, which is an infinite discontinuity. Then the overall limit doesn't exist and continuity fails. Condition 3 fails if f of c is defined and the limit exists, but they are not equal. This is often seen in removable discontinuities where a hole could be filled. In that case, continuity fails. To verify continuity at x equals c step by step, first, evaluate f of c. Does it produce a real number? If not, the function is discontinuous. Second, compute the left-hand limit and the right-hand limit. Do they both exist and are they equal? If not, discontinuous. Third, compare the limit of f of x as x approaches c with f of c. Are they identical? If not, discontinuous. Consider an example. F of x equals x squared minus 1 over x minus 1 at x equals 1. F of 1 is undefined because the denominator becomes 0. So condition 1 fails and the function is discontinuous. Another example, a piecewise function g of x defined as x plus 2 for x less than 2, 5 for x equals 2, and x squared for x greater than 2. At x equals 2, g of 2 is 5, which is defined. The left-hand limit as x approaches 2 from the left of x plus 2 equals 4. The right-hand limit as x approaches 2 from the right of x squared equals 4. So the limit exists and equals 4. However, g of 2 equals 5, which is not equal to 4. So condition 3 fails and the function is discontinuous. A third example, h of x equals x squared plus 3 at x equals 0. h of 0 equals 3. The limit of x squared plus 3 as x approaches 0 equals 3. Since 3 equals 3, the function is continuous at x equals 0. Continuity at a point ensures predictable behavior locally and is a prerequisite for applying powerful theorems like the intermediate value theorem. Functions like polynomials, rational functions within their domain, exponentials and sines and cosines are continuous at every point in their domains. This video about continuity at a point is part of our larger Calculus 1 for Engineering Students course. The course is entirely free and has more than 100 subtopics inside it. We're excited for you to try it, and the link is in the description.